In this lesson, we'll introduce the density for a Gaussian or normal random variable, and we'll examine an important property that defines its higher-order moments. Well, let's begin by looking at the probability density that has a shape that looks like this. That is, its shape is the absolute value for x over the range from -1 to 1. Now, if we generated 1,000 realizations of a random variable with this density and constructed a histogram of those data, the resulting histogram might look like this, which, as expected, conforms to the shape of the underlying density. Now let's see what happens if we average some realizations of this random variable. Here, for example, we show the histogram for 1,000 realizations of the average of 2 realizations of this random variable. Here's what the histogram looks like if we average 3 realizations of the random variable. Here it is for 4, for 5, for 6, 7, 8, 9, and 10. What we're seeing here is that by summing as few as 10 realizations of a random variable, the shape of the resulting density starts to look like the familiar bell-shaped curve, even though, as in this case, we start with a density that is very different from the bell-shaped curve. Now, because many physical phenomena result from the sum of several independent parts, this idea, the idea that the sum of independent variables inherits a distribution with a familiar bell-shaped curve, is one of the reasons that Gaussian distribution is so important in probability theory. Now, the Gaussian density has a mathematical form that looks like this, where the parameter mu is the mean or expected value for the random variable, and the parameter sigma is the standard deviation, and of course sigma squared would be the variance. Now, the Gaussian distribution is also referred to as the normal distribution, and we sometimes use a notation like this to communicate that a random variable x has a normal or Gaussian distribution with a mean equal to mu and a standard deviation equal to sigma. Now, the density for a Gaussian random variable has the familiar bell-shaped curve. Its median and mode are both at the mean mu, and the width extends plus or minus about 3 standard deviations in each direction from the mean, although, of course, the tails of the distribution do extend infinitely in both directions. Now, when we scale and translate a Gaussian random variable, the resulting random variable is a Gaussian random variable whose mean is scaled and translated in the same way that we scaled and translated the variable, and whose standard deviation is scaled by the absolute value of the scale factor. Now, one of the most important examples of this occurs when we subtract the mean from a Gaussian random variable, then divide that result by its standard deviation. The result is a Gaussian random variable with 0 mean and unit variance. And this is very important, and we refer to that distribution, that is a Gaussian with 0 mean and unit variance, as the standard normal distribution. Now let's look at some of the moments for a 0 mean Gaussian random variable. Now, because a 0 mean Gaussian density is an even function, all of its odd-ordered moments will be equal to 0. That is because when we multiply the even density by the odd function of x, the result will be an odd function, and the integral of an odd function is always equal to 0. Now, to examine the even moments, let's begin with the fact that the integral of any probability density is equal to 1. Then, we'll substitute a variable a for 1 over sigma squared so that the density now can be represented in terms of the variable a. Then we'll move the factor of the square root of a to the right-hand side, and after doing that, we'll take the derivative of both sides with respect to this variable a. That result will drop down a factor of x squared into the integral, and then if we cancel the common factors of -1/2 and move the square root of a back to the left-hand side, we'll have an expression that looks like the integral of x squared times the original density, which is, of course, the second moment for the random variable. And because the reciprocal of a is the variance, we get the expected result that the second moment of a 0 mean Gaussian random variable is its variance. Now, if we move the square root of a back to the right-hand side and take the derivative with respect to a again, we'll get x raised to the fourth power inside the integral. Then we can cancel the common term of -1/2 and move the square root of a back to the left-hand side so that we have an integral that is the fourth power of x times its density, which is the fourth moment for the random variable. And because a is the reciprocal of sigma squared, this gives us the result that the fourth moment is 3 times sigma to the fourth. Then we can repeat this whole process again, and by taking another derivative with respect to a, and that will ultimately give us an expression for the sixth moment, which is 15 times sigma to the sixth. Now we could repeat the process and see that the eighth moment is 7 times 5 times 3 times sigma to the eighth, and with a little thought though, you should see that the 10th moment would introduce a leading factor of 9 with sigma raised to the 10th power, and with the generalization of that result, we could get any even-powered moment. Well, if we allow for a non-zero mean, mu, we could extend these results to non-central moments as shown in this table for the first 6 orders. We'll follow up in subsequent lessons with more details about the cumulative distribution and its use in finding interval probabilities.